jumper.
Installing the instrument room fire control safety jumper. Instrument room fire control safety jumper is installed.
The primary and secondary instrument room safety jumper indicates show in. Instrument room, have the arming crew install the instrument room fire line key and rotate to the closed position.
The fire line key is installed and rotated to the closed position.
The primary and secondary T97 key switch indicates show closed.
Arming preparations are complete.
Evacuate to T22.
Evacuating the instrument room.
Seven, 6, 5, 4-stage engine start. 3, 2, 1.
Hi everyone, I'm Megan Carter, Media Specialist for NASA's Space Launch System rocket. As teams at NASA's Kennedy Space Center in Florida are busy getting ready for the first crewed Artemis mission, work continues all over the United States to prepare for future missions as well. One of those locations is right here in beautiful Promontory, Utah, at the Northrop Grumman facility, where I'm coming to you live today. Our partners here at Northrop Grumman have been working to develop a more efficient, lower-cost commercial solution for the boosters for the Space Launch System. As you can see, it is a beautiful day here in Utah, and we are actually just a few minutes away from a hot fire for the demonstration Motor 1 test. The booster motor for today's hot fire is actually locked up on that hill in the test stand right behind me, and it's just about ready to be fired up. The boosters for NASA's moon rocket are the largest, most powerful that have ever been built for flight. And there are 2 boosters that flank either side of the rocket and together produce millions of pounds of thrust at launch. Today, we will get to witness the power of just one of those boosters. But before we kick this off, we're actually going to turn it over to Alyssa Lee in Huntsville, Alabama at Marshall Space Flight Center to learn a little bit more about what we're going to be seeing today.
I am very excited to be here at NASA's Marshall Space Flight Center with a resident SLS and booster expert. Joining me today is Julia Cotobande, the Deputy Manager for the SLS Booster Element Office. Thank you so much for joining me, Julia. We are less than a year away from the launch of Artemis 2, which will see SLS and NASA's Orion spacecraft on the first crewed mission for the Artemis campaign. So would you be able to give us a little quick update on the progress for Artemis 2?
Yeah, so Artemis 2 is currently being stacked at the Vehicle Assembly Building at Kennedy Space Center in Florida. So the twin solid rocket boosters have already been stacked, and the core stage with its 4 RS-25 engines has also been mated to the boosters. We have the Orion stage adapter here at Marshall Space Flight Center ready to ship and be integrated with the vehicle as well. Orion is currently being processed at KSC in the multi-payload processing facility. It's getting its propellants, its consumables, and the launch abort system, and once that's complete, it'll be ready to be delivered to the Vehicle Assembly Building to be stacked onto the SLS rocket as well.
Wow, that's so exciting. It's going to be here before we know it. So as your role as the Deputy Manager for the Booster Office here, what does your job entail? And with that, what are you most looking forward to out of today's test?
So yeah, as Deputy Booster Manager in the Booster Element Office, we are part of the SLS Program Office. And my responsibility is to advise and to assist the Booster Manager in things like programmatic and fiscal and technical planning, procurements, contract actions, DD&T&E, design development, test and evaluation, as well as production and operations of the booster. And this is going to include all of the support equipment as well as the facilities that are needed. What I'm most looking forward to today kind of goes a little bit back into history. When we started the SLS program, in order to save cost and schedule, we implemented the shuttle's proven heritage hardware into our design. But this is being depleted as the Artemis program progresses, and it's just not practical to restart the manufacturing from that 1970s era. So for the last several years, we've been developing what we call the Booster Obsolescence and Life Extension, or BOLE. And so the BOLE is actually implementing new manufacturing processes and new materials from domestic sources. And so this test today is going to be the first full duration, full-scale test of the BOLE motor, which we're calling DM-1 or Demonstration Motor 1.
So how does that tie into the goals and objectives of the test today?
Yeah, so our goals today are to take a look at the performance of the BOLE motor. We are going to be looking at things like the ballistics performance, so the pressure and the thrust versus time, the burn rate of the motor, the pressure drop, the ignition characteristics. We're going to be taking a look at the performance of the internal insulation of the motor, in the case acreage and dome areas. We also have a new carbon fiber composite case, which will be taking a look at its performance during the test, as well as the joints and the seals. We'll be taking a look at our nozzle ablative performance and the electronic thrust vector controls vectoring of that nozzle. And one of the other things that we're demonstrating with the BOLE DM-1 today is that we're able to produce that next generation motor that is high performing, addresses our obsolescence issues, and does it more efficiently and at a reduced cost, which we are realizing a 25% reduction in cost. But going forward, any SLS booster or commercial solid rocket booster is going to need this next generation design because of the obsolescence issues.
Great. Thank you, Julia. That was very enlightening, and I am so pumped to see this thing fire. Speaking of, I think it's time we check back with Megan in Utah to see if we are getting close to this big event.
Thanks, Alyssa. We are now less than 5 minutes away from the hot fire. We're going to take a quick break, and I'm going to get into position to watch. When we come back after the test, we'll actually be answering a few of your questions that were submitted in the chat. But for now, let's get ready to fire this booster up. Just before the test, you are going to hear a countdown from the test conductor, followed by the 2-minute booster firing. Enjoy. We'll see you back here shortly.
This is the test conductor. Report system status.
Support systems are go for static test.
Low speed systems are go.
High speed systems are go. Ultrasonic data systems are go.
TVC systems are go.
High-speed video systems are go. Motor temperatures are go. We are go for BOLE DM-1 static test.
T-minus 3 minutes. Low-speed data operators, begin recording. High-speed data operators, at T-minus 70 seconds, begin recording and report at that time.
Roger.
All low-speed data systems are recording.
Roger. T-minus 2 minutes. T-minus 90 seconds. T-minus 80 seconds.
Test control coordinator, stand by to commit the motor.
Standing by. T-minus 70 seconds.
Commit the motor.
The motor is committed. T-minus 60 seconds.
All high-speed systems are recording.
Roger.
Ultrasonic data system is recording.
Roger. T-minus 50 seconds.
TVC is go for static test.
Roger. T-minus 40 seconds. T-minus 30 seconds. T-minus 20 seconds. T minus 15 seconds. T minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, fire. T plus 5 seconds. T plus 10 seconds. T plus 20 seconds. T plus 30 seconds. T plus 40 seconds. T plus 50 seconds. T plus 60 seconds. T plus 70 seconds. T plus 80 seconds.
Central Support System Operator, enable the deluge, CO2, and quench tool controls.
Enabled.
T plus 90 seconds.
Open the accumulator enable valve.
Accumulators enabled.
T plus 100 seconds.
Activate aft deluge.
Activated.
Whoa.
T plus 110 seconds.
Activate forward deluge.
Activated.
T plus 120 seconds.
Activate head end CO2.
Activated.
Activate quench tool forward command forward. Activate aft CO2.
Activated. TVC power is disabled.
Roger. T plus 160 seconds. T plus 170 seconds. High-speed data operators. Stand by. High-speed data operators, stop recording. T plus 90 seconds. T plus 100 seconds.
Activate aft deluge.
Activated.
Whoa.
T plus 110 seconds.
Activate forward deluge.
Activated.
T plus 120 seconds.
And we're back. In case you missed us before the test, I am live here at the Northrop Grumman test facility in Utah, where we just watched an incredible 2-minute test fire of a solid rocket booster motor for NASA's Space Launch System rocket. I have to say, it took me a minute. I had to recover. That was incredibly cool. So, here with me now to talk about the test and answer a few of your questions is NASA's Dave Reynolds, Program Manager of Booster Subsystems for the Space Launch System, and Northrop Grumman's Doug Hurley, Senior Director of Strategy and Business Development. Gentlemen, thank you for joining me, especially so quick after the test. That was fantastic. This first question is going to be for you. Obviously, we just witnessed something very cool, and that was the first time it had ever been fired up. Can you tell us a little bit about what we just saw, and did you consider it, was it exactly what you wanted it to be?
Sure. Yeah, thanks for having me on and having an opportunity to talk about something that I've been really excited about for a long time. So what we just watched was the most powerful man-rated rocket motor ever tested. It's absolutely amazing what we just watched. A rocket motor putting out almost 4 million pounds of thrust. You can see from the side of the mountain up there, it's still feeling the effects of that test. Yeah, this test is a brand new booster from tip to tail. There's so many things that are different about this booster. It actually has very little relationship to the current boosters that are flying on the Artemis 2 mission that's coming up. And so we were expecting to learn a lot of things, and I guarantee that we're going to spend the next 6 months digging through all of that data and finding out what we need to do. Now, we push the margins on almost every material that we have, and that, I would suspect, is probably one of the first things that we are going to learn, is how close did we come to the edge of those margins. And if we did get too close to the edge that we're not comfortable, we've got other plans in place to move forward and build another motor that can teach us the things that we needed to learn from.
Fantastic, thank you. So Doug, I was actually able to tour a little bit of the facility yesterday, saw a lot of amazing things. One of our viewers is actually asking, what specifically does Northrop Grumman build and test here that's related for the Space Launch System?
Well, we've built solid rocket boosters here for even the shuttle since like the late 70s. So we've been building shuttle heritage, and then of course we transitioned to SLS several years ago, and we've repurposed 8 sets of shuttle boosters that are going to go on SLS.
That's incredible.
So it's an incredible facility, 20,000 acres. So we do a lot of solid rocket motor designing, testing, manufacturing out here much more than just SLS.
Okay. Fantastic. Thank you. So you mentioned a lot of the data that you're going to be studying. One viewer has actually asked, how do you monitor the test? Specifically in the chat, they're wondering about mirrors that are observed to use the to observe the plume.
Yeah, so right behind the motor, right before you see it fire, there's actually a stand that has a mirror in it. Now, obviously, we want to understand how that flame front starts from the beginning of the motor and travels down. And there's no good way to put a camera that's going to survive that test. So what we do is have a giant mirror that sits behind the stand and point a camera at it so that we can see right up the bore of the motor. That tells us two things. First of all, we have a plug that allows us to, first of all, keep the bugs and the dirt out, but also to build up the pressure a little bit before it bursts. So that camera watches to see how that plug is going to break up. But then when that thing breaks up, you can start to see the flame front come down. Now, the mirror doesn't last very long. Once again, pointing to the mountainside, we're going to find it probably tomorrow because it's probably halfway up the mountain. That's just what we expect every single time. But it is one way that we're able to characterize the flame front and how that plug breaks up.
Makes sense. All right, back to you talking about all that power, the propellant. One viewer is asking, what kind of fuel will be used?
So solid rocket motors are typically very similar. We use this ammonium perchlorate, which is a major constituent. We've got aluminum, we've got binders, we have oxidizers. So it's, and when it actually cures in the motor, it almost is like a pencil eraser type feel. I don't know, Dave. I mean, it's really interesting. It burns from the top down. And as we said, almost 4 million pounds of thrust out of this particular engine.
I felt that power.
Yeah.
It was more than I was expecting. I wasn't expecting that at all. It was incredible. All right, so one more question. You mentioned that there are a lot of different things between the current boosters for SLS and the ones we just witnessed. One of those is actually the color. Our current ones are obviously white. This one was black. Does that hold any significance?
So it does. The current boosters that we're flying with right now are mostly metallic. They were repurposed shuttle hardware, but we only have a limited supply of that. And so what we have learned over decades of building solid rocket motors is that a more efficient and faster and cheaper way to build rocket motors is through composite materials. What we used on this rocket was a carbon fiber filament that we wound around a mandrel, and that's why you see it being a different color. It's a dark color, but eventually we would probably end up painting it white because we want to control the temperature a little bit more, and white paint reflects the heat a little bit better. But on this one, we wanted to see exactly how the case behaved, and when you paint it, you cover up a little bit. And so because this is a development motor, and meaning we want to get as much data as we possibly can, that was one reason that we decided to leave it unpainted so that we can have better observation of the case. But composites are the modern way of building rocket motors, and we're advancing in that direction.
Okay. Perfect. All right. Well, that looks like all the time that we actually have here. Any last thoughts? Everybody good? Wonderful.
It was an amazing test.
It was an amazing test. All right. Anything else from you?
No,
all right.
Just glad we had such a great team and crowd here to witness this first test, and it'd be great to see this thing fly sometime soon.
Absolutely. All right. Great. What was the question from off the viewer?
Special about the
yes,
SLS.
absolutely. All right, so these are very special to the SLS and for the Space Launch System rocket. We can't wait to see these fly, and we are so excited that you were able to join us here today. A big thank you to you, a big thank you to Julia and Alyssa for joining us as well. Thank you for tuning in. If you'd like to rewatch the test, be sure to head over to NASA's Marshall YouTube channel. Be sure to also follow our NASA Artemis accounts and Marshall social media accounts for all your SLS related news. And we can't wait to see you for the launch of Artemis 2, the first crewed mission to the moon in over 50 years. Enjoy, and we'll see you soon. Thank you.
Seven, 6, 5, 4-stage engine start. 3, 2, 1.